Yes, sir.
Yes, sir. Sir, could you repeat that? Like, sorry, I'm late. I had some technical
Actually,
issues.
Alan, you are right on time because I didn't say actually anything. I guess Miran, you were trying to say something.
No, no, thank you, sir.
Okay, so last time we did solve just one question related to whatever we have discussed so far in magnetism. Today I will be solving more questions with you, and with each topic where possible, I will be explaining you a few small equations or few concepts as well. So we will begin with this one. Okay, in previous class we solved a question exactly like this. First part was definition of Tesla. Then I hope you remember we have some part like this. Once again, I removed the last part of this question. In both the question, last part is actually related to AC current. So that is very small concept called possible. Many of you remember that the RMS value of current is maximum current divided by square root of 2. So both parts, the one I cropped in the previous class and one I cropped today, is actually related to that. And that part is just 1 or 2 mark question, right? So when we will be discussing that topic, I will surely solve that part with you. Those who got the booklet, this is page 125, question number 5. Right? Start solving it. Once you are done solving it, raise your hand. I will discuss the solution of it. Okay, so start solving it now. Hello. Okay, so I hope almost all of you are done solving this question. Alan, did you try solving it?
Yeah, I did.
Okay. What about you, Amna? Were you able to solve it? Amna, are you there? Okay, now listen. I guess even in last class, I did mention one thing. When in the exam, they ask you to define one Tesla. One Tesla means unit of magnetic field of induction. You could have used any equation to define Tesla, but we always like to answer question in the context of the question. So the question is basically related to this equation. F is equal to ILB sine theta. So our answer should be making reference to this equation only. So from this equation, I can say B is equal to F over I L sine theta. So how we used to define one Tesla? One Tesla is the magnetic field of induction when a force of 1 Newton is applied on a conductor of length 1 meter carrying current of 1 ampere placed perpendicularly to the field. This perpendicular to the field is very important. So your definition should include a reference to 1 Newton, 1 ampere, 1 meter perpendicular thing. If your definition includes all this, then you will surely be getting 3 marks. So how many of you actually mentioned all these 4 things? And of course, you need to mention that Tesla is unit of magnetic field of induction. A horseshoe magnet is placed on a balance. A stiff metal wire is clamped horizontally between the pole as illustrated in figure 5.1. The magnetic flux density in the space between the poles of the magnet is uniform and zero outside this region. The length of the metal, while normal to the magnetic field, so it is perpendicular, is 6.4. When a current in the wire is switched on, the reading on the balance increases by. Now, what I mentioned about this increases by actually gives you the information that the force exerted by conductor on the magnet is in downward direction because this value is increasing. So force on the wire should be in upward direction. Instead, I explain the direction of force on the wire due to this current. So force on the wire due to this current is in upward direction. And why it is in upward direction? Because force on the magnet is in downward direction. Force on magnet is downward. Then you should have made reference to Newton's third law of motion. And how do we know that this force is in downward direction? Because balance reading is increasing. Are you getting the same? I mean, did you mention the same points? Calculate the magnitude of magnetic flux density between the poles of the magnet. So what you will be doing, you will be using the formula F equal ILB sin theta. Right? The value of I is actually given in the question, which is 5.6. Length is 6.4 centimeter, which means 6.4 exponent minus 2 meters. B is unknown. Theta is 90 degree because I did mention the fact that conductor is placed perpendicular to the field. What you will be writing instead of this force? Yes, what should I write instead of this force?
The change in weight.
The change in weight, and that was 2.4 G. So weight is actually given by M into G. That is, by the way, that was 2.4 gram. So you will be putting 2.4 exponent minus 3. The value of G is 9.8. In IGCSE, we used to use 10. In AS it was 9.8 and in A2 we will be using 9.8. This value must be supplied in the list of constant as well. But remember one thing, if you use 10 here, you will surely lose marks. Now, if I simplify this whole thing, what is the value of B that we are getting?
0.065.
0.065 Tesla. So how many of you are actually getting this? Okay, all of you are getting it. Now, just keep on looking at this screen. I need to explain you one small concept. Then we will be solving the next question. Okay, remember in the very beginning, we did mention somewhere that our current carrying wire produces a magnetic field around it. Our current carrying wire produces a magnetic field around it. For example, if this is a wire, current is passing through it in upward direction. So we have already discussed this thing. This wire will produce magnetic field that will be circular in shape. So if I want to draw a line of force, how will I draw? This is the first line of force. Let's say it is circular in shape. This will be second line of force. This is third line of force. Now, I hope you are able to observe one thing. If I look at this element from the top, this is the conductor, just the tip. This is first line of force. This is second line of force. This is third line of force. And let me make another line of force. So let's say this one is next line of force. So what should I have observed? As the distance from the wire is increasing, the radius of the circle is increasing. Moreover, the distance between two consecutive lines is increasing. Are you able to observe this thing? That initially circles are close. Okay, what can be represented by this fact? That lines are going away from each other. If any one of you would like to answer this part.
The density of the magnetic field.
Okay, when lines are going away from each other, it means that density of line of force is decreasing. And density represents strength of the field. It means that field is decreasing. So what I can say, as we move away from the wire, the strength of the magnetic field decreases. That's why what we say, the magnetic field of induction produced by this wire is directly proportional to current. Technically, this is 2I, twice of current. What does it mean? If you double the value of current, the strength of the field will become 4 times. B is proportional to 2I. B is inversely proportional to R, where R is distance of the line from the wire. So you can see, as we are going away, the distance of the line is increasing from the wire. So B is inversely proportional to R. Distance should be decreasing. If I combine these two, it will become B is proportional to 2I over R. When we convert proportionality, we need to put some constant. This is 2I over R. This constant is mu naught over 4 pi. What is this mu naught? I will explain. Mu naught over 4 pi into 2I over R. If you simplify this thing, you will be getting mu naught I over 2 pi R. Whatever we have discussed, this relationship is actually driven by two scientists, and after their name, we call this equation as Biot-Savart law. Biot-Savart law actually gives you the strength of magnetic field produced by current carrying wire. By the way, I have a chance to read a book in which this this equation was something like this. B is proportional to I. They remove that I from here. And instead of using 4 pi, instead of using constant as 4 pi, they actually use constant as mu naught over 2 pi. So I hope all of you will agree that even in that case, you will be ending up with the same result. Did you get what I said? Normally, this equation is written like this: V is proportional to 2i. So when we talk about constant, we write constant as mu naught over 4 pi. So your final result stays the same, mu naught I over 2 pi. This is the actual result. This equation is known as Barton-Savart law. What I have seen in most of the question where you will be needing this formula, question will actually give you this formula as well. That strength of our magnetic field around a conductor is given by this. Because I don't think so this derivation Barton-Savart law is included somewhere in your syllabus, but its application is actually very common. For example, the next question that we will be solving, you will surely be able to use this thing. But in exam, they do ask you to draw magnetic lines of force around the conductor. So remember one thing, you will be drawing at least 4 or 5 lines, and you need to take care of the fact that the distance between 2 successive or consecutive lines should be increasing, right? So if you are getting it, the next question that you will be solving is basically question number 6 of the booklet, page 127. Just give it a try. If you couldn't solve it, I will surely be solving it. And few hands are actually raised. If you people want to ask something, it's fine. Otherwise, put your hands down. Okay. Now answer this question. Once you are
Okay, so let's discuss the answer for this question. Now, what question says define the Tesla? So you must have defined the Tesla. Let me solve this question. Then I will try to define this Tesla by another way that actually suits this question. Now, what question says two long straight vertical wires X and Y are separated by distance of 4.5 centimeter as illustrated in figure 5.1. But by the way, before I explain anything, I don't know whether you got this value of mu naught, that this is 4 pi extra minus 7. What is this mu naught? Remember when we were discussing Coulomb's law, I did use epsilon naught. Remember this? Epsilon naught was permittivity of free space. The electrical behavior of a medium in the field of in the presence of electric field is measured by its permittivity. And the least value is permittivity of free space. So this epsilon is actually permittivity. The magnetic behavior of a medium is defined by a quantity which is known as permeability. That is known as permeability. The least value of permeability is once again for free space. We know the formula epsilon is epsilon r epsilon naught, where epsilon r is the relative permittivity. Similarly, we have an equation which says mu equal mu r mu naught, where mu r is relative permeability and mu naught is the permeability of free space. And the value of mu naught is actually 4 pi exponent minus 7 Weber per ampere meter. Okay, now the long distance, two long straight vertical wires X and Y are separated by a distance of 4.5 as illustrated in figure 5.1. The Y passed through a horizontal card PQRS. The current in the wire X is 6.3 and the upward direction. Initially, there is no current in the wire Y. On figure 5.1, sketch in the plane PQRS, the magnetic flux pattern due to the current in wire X show at least 4 flux lines. So those 4 flux lines should be something like this. We will be having one circle, then we will be having another circle, then we will be having another circle. And what is important, the most important thing is the distance between consecutive circles should be increasing. So last should be further. So you were supposed to draw something like this. How many of you got it right? I mean, you have drawn 4 lines and the distance between 2 successive lines is actually increasing. Okay, next. The magnetic flux density B at a distance x from a long straight current carrying wire is given by the expression mu naught I over 2 pi r, where I is the current in the wire and mu naught is the permeability of free space. Calculate the magnetic flux density at wire Y due to current in wire X. So we need magnetic flux density at wire Y. So what you will be doing, we know that B equal mu naught I over 2 pi X. Mu naught is 4 pi exponent minus 7. The value of current is 6.3 divided by 2 pi, and distance is 4.5. What was given? 4.5. So you will be using 4.5 exponent minus 2 because we always use SI unit. Pi and pi will get cancelled. So if I simplify this entire expression, am I getting 2.8 exponent minus 5 Tesla?
Yes, sir, you're getting that.
Okay, if all of you are getting this answer, now what is next part? A current of 9.3 ampere is now switched on in wire Y. Use your answering to calculate force per unit length on wire Y. So this is wire Y. Now we have current of 9.3. Now we have current of 9.3 ampere in this one. Okay, because of, okay, let me do just one thing. So red color is actually associated to wire X. At this point, the magnetic field of induction, if I draw a circle like this, the point where this wire Y is actually kept, the strength of magnetic field is 2.8 exponent minus 5 Tesla. Previously, there wasn't any current in wire Y, so wire Y wouldn't be experiencing any force. The moment we allow current of 9.3 ampere to pass through wire Y, it becomes a current carrying wire in a magnetic field. So it will experience a force which is given by F is equal to ILB sin theta. So we will be using this equation ILB sin theta. Let me change the color of it so that you can relate. This is for wire X only. Now, what we need to calculate? We need to calculate force per unit length. So it will become F over L equal IB sin theta. Current is 9.3. B is 2.8 exponent minus 5 and theta is 90 degree. So if I simplify this whole thing, am I getting 2.6 exponent minus 4?
Yes, sir.
So I believe all of you are getting this answer, and this is force per unit length. So its unit should be Newton per meter. Its unit should be Newton per meter. Is it clear till here? Amna, are you there, by the way?
Yes, sir.
So are you able to understand this working?
Yeah.
Okay. Miram, were you trying to say something because you unmuted your mic?
No, sir, I was just going to say yes.
Okay. So if all of you are getting it, see, we solved one question in previous session, we solved first question today, and I did mention one thing. Whenever they say define Tesla, what I have seen across the multiple marking schemes, they actually want to see one Tesla in the context of the question. So previously, we kept on using F equal ILB sin theta, and we defined one Tesla. I guess in previous class when we defined one Tesla, it was here. It was a 3-mark question. I think you have noticed it. It was a 3-mark question. When we solve first question today, it is again a 3-mark question because 1 Newton, 1 ampere, 1 meter perpendicular. This 1 meter perpendicular is actually one thing. So that's why this is of 3 mark. Now the question you have just solved, define Tesla. It's a 2-mark question. The first difference you will notice is the number of marks. I strongly believe if you define Tesla the way you were defining, I believe you should get correct all marks because the definition is correct. But in this question, when we discuss this thing, we can define another definition of 1 Tesla. 1 Tesla is actually the amount of force which can, 1 Tesla is basically the magnetic field of induction, which can cause a force of 1 Newton per meter when current of 1 ampere is passing through the conductor. How many of you were actually able to get it? Okay, let me write it here. If I say F equal ILB sin theta, F over L into 1 over I Sine theta equal B. So what we say? 1 Tesla is actually the magnetic field of induction that can generate a force of 1 Newton per meter in a conductor carrying current of 1 ampere placed perpendicularly to the field. How many of you were actually able to understand this definition?
Could you repeat?
Okay, 1 Tesla is the magnetic field of induction that can create a force of 1 Newton per meter in a conductor carrying current of 1 ampere. Is it clear now?
Yes, sir.
Because in this question, we discussed this thing, Newton per meter. And if you look at the marking scheme of this question, they are using actually this technique. So what I will advise you, whenever you find a question like define 1 Tesla, do follow the question. I mean, if they are making reference to that Newton per meter thing anywhere in the question, you can use this technique. Otherwise, what we have used in the first question of today, and the one question that we solved in the previous class, that method is correct. You will find it in number of marking schemes. So you may use any of the method. Okay, last part of the question. The current in the 2 wires in B3 are not equal. Explain whether the force per unit length on the 2 wires will be same or different. The current in the 2 wires in B3 are not equal. Explain whether the force per unit length on the 2 wires will be same or different. Yes, what do you think? Will it be same or different?
Different.
Why?
Because sir, the permeability remains the same and the distance between the separation is the same.
So then how come force is different?
Only current changes.
Okay, current change. Okay, this is answer of an. Yes, Mira.
Current is different, that's why. I'm not sure.
Okay, you said difference as well. Anya?
I'm not sure, sir.
You are not sure. And Samar, what do you think?
Different, sir.
Different. And Alan, what do you think?
They are the same, sir.
They are the same? Okay, why? Yes, Alan, you said they should be the same. So why did you reach this conclusion that they should be same?
Sir, because I don't know, I have feeling like this is not. I'm just predicting. I didn't do it actually, but like.
Okay. Okay, so this is your just prediction that they should be the same. Okay, just focus on this. When wire X exert force on wire Y, and when wire Y exert force on wire X, can I say this is action reaction?
Yes, sir.
So if I can say these are action reactions, so can I say they should be equal in magnitude and opposite in direction?
Newton's third law, sir.
Yeah, this is Newton's third law actually.
Yes,
This
sir.
is actually
Yeah,
Newton's third law.
it will apply over here. Yes, sir.
Yes. Yes, Hania, Miram, Samar, do you think
Yes.
that way?
Yes.
And if any one of you is thinking, sir, we have different amount of currents in each wire. So tell me one thing. If we have a charge of 10 coulomb here, and we have a charge of 2 coulomb here, when they exert force on each other, so do they exert different amount of force because they have different value of charge, or they exert same amount of force on each other? Yes. Yes, Anas.
Same amount.
They exert same amount of force of each other. Though their values are different. Someone can say that 20 coulomb should exert more force. No. because the force is proportional to product of the charges. So no matter what, they will be exerting equal amount of force on each other. Similarly, the force exerted by wire X on Y should be the same as force exerted by Y on wire Y on wire X. I can explain it further. The easiest approach is these two forces are action-reaction pair. And according to the third law of motion, action reaction are always equal in magnitude, opposite in direction. So these two forces should be equal in magnitude. If you want to make it little complicated, you can do it, but you will be reaching the same result. See, F is equal to ILB. Okay, let me do one thing. Let me draw the two wires. I guess you will understand easily. This is wire 1, right? Whose length is L, current is I1. So it will produce a magnetic field. That magnetic field will appear something like this. So strength of magnetic field at this point will be B1. So if I say calculate B1, okay, this distance is actually R. So if I say calculate B1, you will use mu naught I1 over 2 pi R. Now what I did, I took another conductor and I kept it at this point. So length of this conductor is the same, L, but amount of current in this conductor is different. That is I2. It produces a magnetic field. That magnetic field should be something like this. Since its current is different, so strength of the magnetic field at this point should also be different. That strength should be B2. But distance will remain R. I hope all of you will agree, sir, distance is R. So the value of B2 is actually mu naught I2 over 2 pi R. So both current carrying wires are actually producing magnetic field. The fact is, blue conductor will experience force because of B1, and the red conductor will experience force because of B2. Do you people agree? That red conductor is actually experiencing force because of the magnetic field set up by the blue conductor. And the blue conductor will experience the magnetic force set up by the red conductor. Let's try calculating that force. So if I need the force experienced by blue conductor, so I call it F2 because blue conductor is 2 near me. This is 2, this is 1. So F2 is I2 L, it should be B1. Since they are placed normally, I'm not mentioning sine theta, right? Just put the value of B1. What will you get? I2. I'm interested in force per unit length. So I2 B1 is mu naught I1 over 2 pi R. So F2 over L is mu naught over 2 pi R I1 I2. Let's calculate the force experienced by the red conductor. For that, you will write this formula. F1 should be I1 L B2, right? Put the values. F1 over L equal I1 and B2 is mu naught I2 over 2 pi R. So you will surely agree. So F1 over L is actually mu naught over 2 pi R I1 I2. So it means that force per unit length actually depends upon the product of I1 and I2. Because mu naught over 2 pi R will always remain the same because the distance of first wire from second wire and distance of second wire from first wire, they are actually the same thing. So it means that the force per unit length is proportional to I1, I2. isn't it exactly like force proportional to product of the charges? So 10 coulomb will exert same force on 20 coulomb as 20 coulomb exert on 10 coulomb. Is it making sense?
Yes, sir.
Yes, Alan. Are you getting it? Because all other hands are actually raised, so I'm assuming that all of you are getting it.
Yeah, I'm getting it, sir.
Okay, so this is a difficult way, but I feel this is something if you mention in the answer, nothing like it. Because here there are two y's, x and y. So what I can say, one answer is action reaction thing. One is action reaction. So force should be same. Alternatively, what you can say, force is proportional to product of current in x and y. So it means that force will be the same for each other. You could have expressed your answer anyways, but I thought to explain this part as well to make things little better for you. Okay, if you are done solving this question, the next question that we can solve is okay. Now look at this screen. Let me explain you one more thing. Remember when we were discussing B, what is the name of B? It is one is magnetic field of induction. I guess in last class or in last class, I did try explaining. Why do we call it magnetic field of induction. The other name of this B is magnetic flux density. Now, from where this name actually came? Let's say we have a surface. That surface is kept like this. And we have magnetic lines of force which are passing through the surface like this. The total number of magnetic lines of force passing perpendicularly through the surface. If you look here, all these lines of force are passing perpendicularly through the surface. These lines of force are collectively known as magnetic flux. Because the word flux actually means flow of something. The flux actually means flow of something, right? So when we talk about water current, water flux, it means that flow of water. So magnetic flux means flow of magnetic lines of force. The total number of magnetic lines of force passing perpendicularly through the surface. Okay, let me write here. The total number of magnetic lines of force passing through a surface perpendicularly is called magnetic flux. So first thing, we should be knowing what is magnetic flux. Mathematically, magnetic flux denoted by Greek letter phi. I hope many of you are aware of this symbol. This is known as phi. Magnetic flux is given by B delta A cos theta. Magnetic flux is given by B delta A cos theta. This delta phi is called flux. This B is called magnetic field of induction. Delta A is actually area of the surface, and this theta is actually angle between B and area. Remember one thing, area is a vector quantity and every vector has a direction. So how will you identify the direction of a vector? It is said that area of a surface is always perpendicular to the surface. Area of a surface is always perpendicular to the surface. For example, if you talk about this surface, its area should be something like this. This is area. And this is the direction of field. May I know what is the angle between B and A? If any one of you can answer this.
0 degrees.
0 degree. And what is the value of cos 0?
1.
1. The value of cos 0 is actually 1. That is why if B is parallel to area or B is perpendicular to the surface, both are one and the same thing. It means that theta will be 90 degree. In fact, it means that theta will be 0 degree. If B is parallel to area, it means that B is perpendicular to the surface. You can see in this diagram that B is perpendicular to the surface. That's why it became parallel to area. So theta is 0. In such condition, if we calculate the flux, that flux will be maximum. Why maximum? Because cos 0 is actually 1. What if B becomes perpendicular to area or B become parallel to surface? In this condition, theta will be 90 degree. And we know that cos 90 is actually 0. So the flux will be minimum and it will be 0. If any one of you is unable to visualize this thing, so let me do just one thing. So this is the case where they are perpendicular. Now, if in the exactly the same case, what I do, if I consider the same case here, the only difference is the surface is actually parallel to the line of force. The surface is actually parallel to the line of force. So if you look at the area will become like this. Now area is perpendicular to line of force. Do you agree? Because area is always perpendicular to the surface. So when surface and field become parallel, area and field become perpendicular. So angle is 90 degrees. So this time angle is 90 here. When this angle become 90 degree, what will happen? Theta become 90 cos 90 is 0. Flux becomes 0. And it makes sense because no line is passing through the surface. Flux means number of line of force passing through the surface. If field and surface are parallel, no flux will be passing through the surface. Is it making sense? Yes, Samar, Alan, are you people getting it? Okay, if it is
Yes.
clear till here, one last thing. If you look at this thing, this equation, if I say drive equation for B, what you will say? B is flux over area. Remember, anything divided by size is known as density. So this is flux divided by area. So can I say this is flux density? That's why this B is also referred as magnetic flux density. Are you people getting it? In previous classes, I used to call it magnetic field of induction, but I guess in today's question somewhere, we used the term magnetic flux density. Yeah, here. Magnetic flux density. This name actually came from this definition that B is actually flux over area. If any one of you is wondering, so why are you using that delta? Remember, what does this delta mean in science or physics? Any one of you?
Small change.
A small change. That delta actually represent a small change. Remember the concept, I did try explaining it. Do we have electric field intensity for the entire field or for a point of the field? I'm
Point
making
of the
reference to
field.
electric field because you can understand easily. Electric field strength is of the field, is not of the field. It is actually of the point of the field. So if we take a larger surface, intensity won't remain the same. This is exactly happening with the magnetic field as well. If we are taking large area, magnetic field won't remain the same. To keep the magnetic field same, area should be very small. So we calculate flux over a small area so that we can have only one value of V that we can put in the equation. So this delta actually referring to a small change. Anyways, if everything is clear, now this is question number 3, page 120. Those who got the booklet, try to answer this question. Once you are done with it, let me know. We will discuss the answers. And the hands which are actually raised, please put your hand down so that once you are done solving it, you may raise it. Yeah, I guess many of you are still solving. Do complete this question before next class. We will start next class with the solution of this one. Then we will be discussing few more topics like Hall probe and magnetic, in fact, electromagnetic induction. So do complete this question before next. Anas, are you done? Because your hand is actually raised.
Yes, sir.
Okay. So you need to wait for the answer for next class. So we will resume from here in next class.